Okay, all right. Thanks so much, and sorry again about the technical hiccup. So, okay, so we were investigating what happens when we integrate 1 over z minus a, right, around the circle. So the circle is definitely a closed curve. The circle also doesn't contain a, right? Of course, the ball inside contains a, and so, but the circle itself doesn't, right? And this function, of course, is very nice. In the right, there's no, the issue of it is in a, but in the circle, it's a perfectly nice function. But let's see what happens to this integral. Okay, so let's take the integral over the circle. I think of the circle as being counterclockwise. Okay. And let's integrate 1 over z minus a dz. Okay, so what is this? Right? Let's do the definition. So let's parameterize the circle. Maybe I should parameterize the circle here and then go back there. Right? What's a nice way of parameterizing the circle? We'll just take zt, right, to be, well, it's centered at a, and then I just go around the circle with the exponential, right? With, of course, radius r. Right? All these points, when I subtract a, they have modulo r, right? Modulos r, and right, and so t, and you run around the circle, and t needs to go between 2 pi and 0. Okay, so let's go back now over here. Okay, so let's do this calculation. Okay, so we have the integral from 0 to 2 pi, right? 1 over z minus a, so we just have to use the parameterization, right? So z is a plus r e to the it, right? Minus a times the derivative of z with respect to t dt. Okay, but what's that? Right, so what's this derivative? Well, this derivative is just r times the derivative of this is I times e to the it. Right, so we get r, and then I comes down from the it. Right, this is the derivative of z over a, right? A plus r eit minus a, so the a's cancel out, get e dt. Okay, we're almost there, but now all this stuff cancels out except the I. And so this is equal to 2 pi I. Okay, this is one of the most, very simple, but one of the most important calculations, I think, or the most, not important as in the sense that will give us something just by itself, but in a way that it illustrates a very important phenomenon. Okay. And the point is that, right, even though the issues with this function are not, the curve doesn't go through them, they are in the interior of the curve, and this creates a problem. And we're going to explore exactly and try to come up with definitions of exactly what that means and what we have to start talking about when a point is inside the curve and things like this. And if you think again about this issue with the log and being single valued, right, this is exactly the kind of thing you would expect, right? Because if you go around the circle, then if you think of the fundamental theorem of calculus would tell you that it's like the log somewhere minus the log when you go around and are back in the same place. right? But remember the log, right? We don't know how to define a single valued in the whole complex plane. And if you think about it, it has this part that's the argument, right? So when you go around, it goes 0, it increases and comes back as 2 pi, right? So the imaginary part will do this loop and show you a 2 pi I, which is exactly what you get here, right? Of course, what I just said is not a mathematical proof, while this is, but it's good to think intuitively at why one would actually expect this, okay? And this means in particular that we cannot define the log single valued in annulus around A, right? So log of Z minus A cannot be defined single valued as a single valued analytic function in an annulus around A. Right, so what I mean by this is something like Z minus A between a small radius, small, and a large one. Okay, because otherwise you would get 0 in this integral. Okay, however, there is a place in which we can define the log in a single valued way. Okay, maybe before I get there, let's see how the quality is. Let me look at the chat. Okay. Seems like it's not working so well. But is this the microphone that's working on YouTube? Or did I like put a wrong microphone? Test. Is it this one? All right, I'll switch to the other one after the break. I'll have to figure out what's the problem with the receiver, but that might take a while, and so I don't want to do it during lecture. Yeah, the other microphone is better for sure. Okay, other questions? Let's see. No, there's no reason for the logarithm to be with a capital letter. I just write it that way, but yeah, there's absolutely no reason. It's the same function. Okay, however, it is quite easy to define the log single valued in a half space, for example, right? So if my domain gamma omega, sorry, is a half space, say half space, not containing A, then it's easy to do it single valued, right? Proof by picture, right? Take A here, think of A here, right? And now take a half space, right? So this. Right, then of course, log, right? We know that log Z minus A should be what? Should be log, the real log of the modulus plus I, the argument, right? And the issue comes from the fact that, the argument is an angle, and when you go around, you should go to 0, but you go from 0 to 2 pi, and then it becomes 0 again, right? That's the issue. Right? But this issue doesn't happen if you never get to go around, right? If you never get to go around, you never have this problem. And let me see if I can find another color. And so in particular, if you have a point here, right, you can just, the arguments that you're going to see are you never have to go around. So you can just take this argument to be, say, between pi and minus pi. Right, because you're never going to go past, right? You're never going to get to this side. And in fact, you're never even going to get lower than minus pi over 2 or above pi over 2. Right, and so there is no problem in defining. You can just define in this branch, or I mean, even others, right? You could take right? Really, it's only between even less than minus pi over 2 and less than pi over 2. Right, and so because of this, there is no problem in defining the log on this half space. And so this means in particular that if I have a curve, let me try to use yet another color, right? If I take a curve like this, right, then the integral of gamma of dz z minus a should be 0. Right, because there I can take the log is the primitive, and there's no issues with it not being single valued. Okay, so let me draw the picture here before I go on. Because this is I mean, it feels like I'm doing a lot of, simple calculations with just a particular function. But this illustrates a point that is important and illustrates it in a setting where we can actually, get our hands dirty and do some calculations, right? But what this suggests, and just foreshadowing a little what's yet to come, right? That if I have a point A, right, and I'm doing integrals of, right, dz z minus a, and I have a point A, then if I take a curve, we don't quite know yet for every curve, but at least if I take a curve like a circle, then the integral on this one, right, on the circle of this function, dz z minus a, right, was 2 pi I. It's kind of clear that if I go around twice, if I just integrate on the circle and the circle again, I should get twice that, right, just by linearity of the integral with respect to composing the curves. On the other hand, if I have, right, if I have a curve, let me use again the green, right, if I have a curve that sits here, right, that's all in one side of the half, in one, right, in a half space, right, I should, to be more precise, right, what's happening here is this is inside the omega, a half space not containing A, right? And so if I have a curve like this, then this integral is 0. Okay, so there's two extremely important, I wouldn't say implications because they're not mathematical implications yet. They will be, but there's two really important ideas that come from here, right? Or that are very, I think, very clearly illustrated here. One is that this integral feels, at least in a way, we haven't quite made this super clear yet, but certainly this integral, it's feeling like it has the power of telling me how many times a curve, or let me say it before even simpler, it feels like this integral is having the power to tell me whether a curve goes around a point A or not. We don't yet know this because, right, I've only shown it for the circle. If I have a wiggly circle, I haven't done that calculation. I haven't argued that precisely. Also, I might have a curve that does not go around A, but still is not in a half space, right? So we haven't quite argued this just yet. But it certainly is feeling, and if you think about it, that this integral gets to see whether a curve went around A or not. And this turns out to be an extremely powerful idea because it allows you to describe geometry and topology, properties of a space, via calculating integrals on it and integrals of curves on it. And this is the key. And in particular, if you think of curves and if you think of adding curves as composing curves, right, taking one curve and then the other, then it's, I don't know, easy, but not so hard to imagine that now this allows you to put some kind of algebraic structure in a space, right, in a topological space or in a region in a complex plane, right, in which if you have a point, you can take curves and count how many times they will go around a point. And when you add two curves, then the number of times they go around a point should be the sum and so on. And it's exactly this algebraic structure of this type that you can put on the domain or more general in the topological space that gives rise to algebraic topology. Okay, so you'll see, maybe you've seen a little bit of this in algebra this semester. You'll definitely see this in topology next semester. And if you take more advanced courses in algebraic topology, that's sort of what, I mean, in a sort of reductive way, this is what it is all about. Okay, so that's point one. It allows, right, seems to have the power of, I won't write because I haven't actually proven that it has this power, but I just want you to intuitively see it, right? So that when we go prove it, you feel motivated to see why we're doing this in the first place. Another power that this has, and maybe that's even less clear at the moment, but it's actually what we're going to use a lot, is the fact that if now I massage this function, this integrand, just a bit, so if I make this integrand in a way, then when I take the integral and I go around the point, I get not just 2 pi I, but instead I get some information about a function. Okay, this might feel a bit more surprising at the moment, but okay, try to imagine. If I massage now this, if I make a slightly different integrand, in a way that instead of having here 2 pi I collect information about the function f at the point A. It's not so hard to imagine that maybe I can make up something like this. Then I get what's called an integrand formula. Right? These are extremely useful in studying of differential equations. You may have seen this before. But once I'm able to do that, it will allow me to say something about the function value at A of a function, given some kind of integral on a curve around A. And this is key to almost everything in complex analysis, in the sense that this forces a tremendous amount of regularity, right? Because this means that as long as the function is nice in some curve, it also needs to be nice on the center and things of this type, right? Very much how, in physics and in modeling physics and differential equations, when you have something like diffusion, right? And again, recall the connections between diffusion and harmonic functions, which are the solutions to that, and complex analysis, where we saw that the real part and the complex part, because of Cauchy-Riemann, needs to be harmonic, right? So this is all connected. How in diffusion, when you force the boundary, right, of some kind of diffusive process to stay fixed at a certain concentration or temperature or whatever, that it's kind of intuitive that the center needs to be sort of an average of what's in this boundary in some form, right? And then this forces a lot of regularity, and harmonic functions are extremely regular and so on. And we're going to be able to exploit all of that to get information about what's inside, what's the function at a point from some kind of integral of the function around. Okay. So this is sort of two foreshadowing. I mean, this is like a teaser to the future. Right? It will allow us to see, or to count, or let's say see, if a curve goes around a point. And I haven't proven any of this, and it will allow some form of an integrand function, an integral formula. Right? That is the celebrated Cauchy integral formula. Okay, so again, I didn't prove any of this that I said. I'm just trying to give you some intuition of what we're going to do in the next few lectures, right? With the intent that to just see the proofs and the theorems and the proofs, you can and should read the book from from the comfort of your sofa. And so I'm trying here to give you some kind of foreshadowing intuition of why we're doing what we're doing and what kind of things go into play. I guess, because of the current situation, you also can watch this lecture, and you should, from the comfort of your sofa, but hope it's still a little bit different. Okay. So let's see. Okay, so let's start with, I think we're now ready for Cauchy's theorem. Okay, so let's start with Cauchy's theorem, one of the main players in the course. Okay, let me first offer an informal version of it, and then we're going to go build to it to very formal versions of it, step by step. Okay, so if omega, a region over the complex numbers, is nice enough, and this nice enough is actually very strong, we'll see. Part of what we're going to do in the next week is trying to understand exactly what one means by nice enough. An F is analytic in omega. Then the integral of over a curve of FZ ZZ is 0 for all this closed curve in a closed curve inside omega. Okay, so the informal version of Cauchy's theorem, this is the aim, right? Maybe we'll spend, I don't know, maybe a week or a week and a half doing this. The point is that it's really important what one means by nice enough, right? So recall that, you know, the integral being 0 over closed curves is the same thing as it not depending on anything but the endpoints, right? This was equivalent, and this is what is going to allow us then to transform, right? If we have something like this, then it can allow us to transform results like what I was foreshadowing before into actually precise mathematical statements. But we really have to understand what one means by nice enough, right? And in particular, right? So just as a warning, right, before we go on, right? Taking omega to be the complex numbers without, say, 0 or without A is not nice enough, right? Is not nice enough for the sake of, right? For the sake, I mean, okay, this in pink is not super precise for the sake of Cauchy's theorem. And you know, if you think about topologically, right, and even geometrically about this set, it's a very nice set. Right? It's definitely connected, right? From any point in this set, I can reach any point. Right? I might have to go around A, but I can definitely reach any point from any point. Okay, so from any sort of, I would say, local, maybe let me use the word local, from any kind of local properties, this set is extremely nice, right? Around every point, there is a neighborhood, you know, it's an open set, it's connected, and all of this. But somehow is not nice enough for Cauchy's theorem, right? The point is that it has a hole, right? And so, you know, as you may know by now, topology likes to study holes of spaces. And what the point is that topologically, this space is different from just the whole complex number because of this hole. And this is one way in which we're going to really see this difference, right? And then this difference can be exploited even to understand topology. Okay, so basically, as we're going to go into this path of attempting to prove Cauchy's theorem, we're going to do it by starting with very, very simple regions. Okay? And, you know, there's a few ways now of doing this. You can say, okay, what is the simplest region? Maybe it's like a triangle or rectangle or a disk or something like this, right? And you can try to prove for basic regions like this. We're going to start with a rectangle, but maybe before I even start with the rectangle, I want to just motivate why one would start with a rectangle, right? I would argue that it's maybe not just because it is one of the simplest possible regions, because it's easy to understand. But the point is, if you remember, okay, so now instead of foreshadowing, let's go look a bit in the past. If you remember this proof, right? So let's do a bit of recalling, right? So recall. Remember the proof when we said that that if right that if that having a primitive was equivalent to, having a primitive was equivalent back even when we were talking about functions in the real numbers, that having a primitive was equivalent to the integral not depending on the path, right? And so what we did was we had this px plus q dy, and we asked whether this was equal to some some du, right, some exact differential in that language. And what we did in order to argue that if something didn't depend on the path, then there must be a primitive, is we said, okay, we start with the point x0, y0, and we aim to get to a point x and y, right? I mean, you can replace this by just z0 and this by just z. I'm just trying to use the language that we used before. Right? And then what we said was, well, we could integrate it. We could go there by going like this, or by going around the green path instead. Right? And if we defined, right, and then we would define, right, we defined u. Let me use this white. Right? We defined u. I'm not yet proving anything. I'm just giving some intuition. We defined u as the integral over this path, right? Either the blue gamma or the green gamma prime, right? Of the function of px, pdx, q dy. And we said that then when we, because there was independence of paths, this was well defined regardless if we did it over gamma or over gamma prime. And if in the end you were going up like this, you could see that the derivative with respect to y, just because of the fact that, over r, the derivative of the indefinite integral is the integrand, then would have to be actually, right, q in this case, right? But it would have to be whatever function we're integrating this way, right? And if you were on the green curve, you could see the derivative with respect to x needed to be, in this case, p, right? And this gave you that, because the integral is the same for any curve like this and any curve like this, that immediately you get that there must be a primitive, right? This is the proof that we did when we showed this equivalence. But if all you have to argue is that you can make a picture like this, then really what you're saying is that the integral around the rectangle, right? You can think of this as a rectangle, r, and that the integral around the rectangle is always 0, right? Because you can view as you integrate in this curve and here, and then you integrate back on gamma prime. And so if I'm able to prove Cauchy's theorem for rectangles, I can sort of slowly recreate that proof that we did before, and we'll do that. Because once I have that the integral is 0 for rectangles, I can start building primitives in exactly the same way, right? And so for that reason, starting with rectangles is sort of, we have to prove it for rectangles, and that will require an idea. But once I have it for rectangles, I have the hope of starting to build primitives this way, right? Because I can construct curves in which this part shows me a derivative in y, and this one shows me a derivative in x. Okay, so this was all a lot of intuition. We're actually going to prove it in the next, after the break. But I want you to, I don't want the arguments just to come as sort of magic. Right? I know that by now they've been, dissected and for many years, and this gives, right, and so they're presented all very cleanly, right, which is maybe not the case if you study a more something that hasn't been known for this long, but I want you to think about, like, why would one be interested in proving such theorems? Why start with this and all of that? And so I'm trying to give you some intuition of why it makes sense to start with rectangles. And what we're going to do after the break is prove this theorem for rectangles. And then we'll move on from rectangles to more and more complicated spaces and regions and subsets. Okay, thanks so much. I'll try to fix the problem with the microphone during the break. Sorry for the issue.